Welcome to the Deep Dive Lab. We have a seriously fascinating deep dive today, looking at some incredible new material science. But before we jump into the sources, I actually have a tiny grievance to air.
Oh, all right. You are in the trust tree here. Lay it on me.
It is a small thing, a petty thing, really, but
Yeah.
it has been driving me absolutely crazy for years.
Let us hear it.
It is the ultimate betrayal of the plastic fork.
Oh, the plastic fork. I know exactly where this is going.
Right. Like you are at a backyard barbecue, the sun is shining, you grab a paper plate and you load up on potato salad and maybe a nice piece of grilled chicken. You grab that white plastic fork, the handle, solid, rigid. It feels like you could build a suspension bridge out of it.
Completely indestructible handle.
Exactly. So you go to take a bite, you stab the chicken.
It just snaps.
It snaps. Or worse, the tines just bend sideways like overcooked noodles. And you are sitting there holding this perfectly rigid handle, looking at the useless mangled end, thinking, why? Why is the part I hold strong, but the part that actually has to do the work is weak? I mean, it is the exact same piece of plastic.
It is a betrayal.
Yeah.
It really is. But honestly, your barbecue rage is the perfect entry point for what we are unpacking today. You have essentially stumbled upon the fundamental flaw of modern manufacturing.
Well, I knew my anger was scientifically justified. It is not just me being hangry.
No, it is a real issue. Engineers call that monolithic manufacturing. Basically, when you make something out of plastic, whether you are injection molding a spatula or 3D printing a bracket, you are forcing that material to be just one thing.
Like it has to pick a lane.
Exactly. It is either all hard or it is all soft. You cannot have a fork where the handle is rigid plastic and the tines are made of, say, indestructible diamond unless you physically glue them together.
Which brings up my second grievance. Action figures.
Oh boy.
Hear me out. I remember having this Batman toy as a kid. His chest was hard plastic, his arms were hard plastic, but then his cape was also this weird, stiff, awkward sheet of hard plastic that just got in the way of everything.
The Lego movie problem.
Yes, the Lego movie problem. Everything is awesome, sure, but everything is also just a block.
Right, because traditionally you have a vat of liquid plastic. You cure it, it becomes a solid. You do not get to tell the molecules, hey, be soft on the left side and hard on the right side. That is asking way too much of the chemistry.
But imagine if you could. Like, imagine if you could print that Batman figure and the chest plate is armor hard, but the cape actually flows like fabric, and it is all made out of the exact same liquid at the exact same time.
Like the T-1000 from Terminator 2?
Exactly. Just shifting properties on command, liquid metal style.
Well, that sci-fi dream is basically what our source material is about today. We are looking at a groundbreaking research paper published in the journal Science, so you know it's the real deal. And it effectively rewrites the rulebook on 3D printing.
I am so ready to have my mind bent. Let us get into it. What are we looking at?
The paper is titled Lithographic Crystallinity Regulation in Additive Fabrication of Thermoplastics.
Okay, that is a mouthful.
It is. So the researchers thankfully gave it a very cool acronym.
Cree-craft.
Ooh, craft.
Yeah.
I like that. It sounds artisanal, like we are making sourdough starters but with high-tech lasers. Yeah, it stands for Crystallinity Regulation in Additive Fabrication of Thermoplastics. And we need to give credit where it is due because this was a massive collaborative effort.
Who is behind it?
It was led by Alex J. Camiso from Sandia National Laboratories, along with Zachariah A. Page from the University of Texas at Austin, and Samuel C. Leguizamon, who is actually affiliated with both Sandia and Arizona State University.
Okay, so we have the heavy hitters from the national labs and major universities teaming up here. This is not just a hobbyist tinkering in a garage.
Far from it. This is absolute cutting-edge material science.
All right, so before we get into the how, because I know the chemistry is going to get a little wild, let us set the stage on why this is such a huge deal for the listener. We mentioned the fork and the Batman cape, but what is the industrial version of this problem?
Think about something you use every day. A toothbrush or a power drill. A good toothbrush has a hard plastic handle so you can actually grip it and scrub, but it often has those soft rubbery grips for comfort. Or think of a power drill. It has a hard casing to protect the motor, but a soft overmold where your hand goes so it does not vibrate your bones apart.
Right, and I assume to make those, they just make the hard part and then dip it in rubber or something? Or glue it?
Basically, yes.
Yeah.
It is called overmolding or multi-material assembly. You're taking two chemically totally different materials and trying to bond them together. And that creates two really huge problems.
Let me guess. One is that they break.
Exactly. The interface where they touch is a natural weak point. That is where it is going to peel or snap.
I have definitely had the rubber grip just slide right off a screwdriver before.
Right, we all have. But the second problem is actually much bigger on a global scale. Recycling.
Because you cannot melt them down together.
It is a total nightmare. You have to mechanically separate the rubber from the plastic to recycle it. If you throw a multi-material object into a recycling grinder, you just create contaminated trash. You cannot make a new toothbrush out of a weird mix of hard plastic and soft rubber.
So it just goes to a landfill.
Mostly, yes. So the holy grail of material science has been this question. Can we take one single vat of liquid resin and print an object that is hard in some spots and soft in others without ever changing the material?
Because if you can do that, you solve the peeling problem since it is one continuous piece, and you solve the recycling problem because it is just one chemical.
Precisely. And according to Camiso, Page, and Leguizamon, the answer to that question is finally yes. This is where we get into the magic of Conifay.
Okay, let us talk about the magic, though I assume it is actually just very complicated chemistry.
It is chemistry, but it feels like magic. The secret ingredient here is a polymer called polycyclooctene, or ПCOE for short.
ПCOE, okay, I am writing that down mentally.
And they mix it with a very specific catalyst, which is ruthenium-based. Now, to understand how this actually works, we have to talk about a concept called crystallinity.
All right, I have my mental notebook ready. Let us unpack crystallinity. Because when I hear crystallinity, I immediately think of diamonds or quartz. But plastic is not a rock.
No, it is not. But at a molecular level, it follows very similar rules of organization. The best way to visualize this for anyone listening is what I like to call the spaghetti theory.
I am always here for a food analogy. Let us hear it.
Imagine a box of dry, uncooked spaghetti. You open the box. What do those noodles look like?
They are perfectly straight. They are packed tightly together side by side, all lined up in the exact same direction.
Exactly. There is very little empty space between them. That represents high crystallinity. When polymer chains, which are the long molecules that make a plastic packed tightly and aligned perfectly like that, the material is stiff, it is strong, and it is usually opaque.
So like a milk jug.
Spot on. That is high-density polyethylene, or HDPE. Strong and rigid. Now take that same spaghetti, throw it in a pot of boiling water, cook it, and dump it into a bowl. What does it look like now?
A total mess. Tangled, chaotic, looping over each other, just zero order at all.
Right. That is low crystallinity, or amorphous. When the chains are disordered and tangled, they can actually stretch and move past each other. That makes the material soft, flexible, and usually clear.
Oh, like saran wrap.
Exactly. That is low-density polyethylene, or LDPE. So in the real world, HDPC and LDPE are chemically very similar, but their structure, their spaghetti arrangement is different. One is organized and one is chaotic.
Okay, so the goal of this SIRAF technology is to somehow tell the 3D printer, hey, make this part of the object like uncooked spaghetti so it is hard, and make this part like cooked spaghetti so it is soft.
That is exactly the goal.
But how? I mean, if it is all sitting in the same liquid vat, how do you control the cooking method on a microscopic scale?
This is the twist that makes this paper so fascinating. They control it entirely with light.
Light, like shining a flashlight on it. Specifically the intensity of the light. They use a projector to shine a grayscale image onto the liquid resin. So some pixels are a dim gray and some are bright white.
Okay, hold on. Usually with 3D printing, I think it is called stereolithography, right? Light cures the plastic. It hardens it.
Correct.
So I am guessing more light, meaning more energy equals harder plastic. Like baking a cake for longer makes it tougher.
And that is exactly what everyone assumes.
Yeah.
That is where you would be completely wrong.
Really?
That is what makes this so counterintuitive. In this specific chemical system with the ПCOE and the ruthenium catalyst, blasting it with bright high-intensity light actually makes the material softer.
You are kidding. You blast it with energy and it ends up softer. That sounds entirely backward. That is like saying if I cook my steak on a hotter fire, it stays raw.
It does feel totally backwards. But here is what is happening at the molecular level. Remember that ruthenium catalyst I mentioned?
The secret sauce. Right. Its job is to facilitate the reaction to link all the molecules together. In low light, dim light, the catalyst is happy. It works slowly. It slowly builds these long polymer chains, and because it is happening so methodically, the chains actually have time to straighten out and pack neatly together.
Uncooked spaghetti.
Uncooked spaghetti, high crystallinity, hard plastic. But if you hit that catalyst with high-intensity bright light, you basically overstimulate it. You force the reaction to happen way too fast.
Oh, like rushing through a job and making a mess?
Exactly.
Yeah.
It freezes the molecules in place before they can organize themselves. The reaction creates what chemists call cis-isomers, which are basically permanent kinks in the chain.
So the bright light forces the molecules to stay kinked and tangled up.
Yes. It freezes them in that cooked spaghetti state.
Oh,
So
great.
dim light gives you a hard rock, bright light gives you soft rubber, and everything in between all the shades of gray gives you something perfectly in the middle.
That is wild. So just by changing a single pixel from gray to white in the printer software, you fundamentally changed the physical reality of the object from hard to soft.
Instantaneously.
Yeah.
No changing nozzles, no injecting a second material, no glue, just pure light intensity.
Okay, seeing is believing. And the paper in Science has some absolutely incredible examples of what they actually built with this to prove it works. We have to talk about the turtle.
Ah, yes, the Burmese star tortoise. This is such a great demonstration of the tech.
So they printed a model of this turtle, and looking at the photos in the paper, it just looks like a standard little plastic toy. It's a little gray turtle. But if you were sitting there and you actually picked it up,
If you picked it up, you would feel that the shell is completely rigid. It is hard. It protects the animal just like a real biological shell. It is highly crystalline. But the legs and the head, they are soft and squishy.
and that was all printed at the exact same time.
One single print job, one vat of liquid. They just projected a digital pattern where the light was very dim over the shell area and very bright over the legs.
That is so cool. It is like they printed a toy that is already articulated, but there are no hinges.
No hinges, no weak points. And it gets even more complex than that. They also printed a model of a human hand.
Now, this one completely blew my mind. Because a hand is not just hard and soft, right? It has gradients. It has layers.
Right. Think about your own hand. You have bones, which are rigid. You have skin, which is soft. But then you have all these tendons and ligaments, which sit somewhere right in the middle. They are tough, but they are flexible.
And they actually mimicked that.
They did. They printed a hand where the bones were made with very low intensity light, so they are rigid. The skin was high intensity, so it is soft and pliable. And the ligaments connecting them were done with a medium gray light, giving them that perfect tough elasticity.
That is literally mimicking biology. Nature does not use superglue. Nature uses gradients. Your tendon turns into bone gradually. It is not bolted on with a screw.
Exactly. And that is exactly why biological structures are so incredibly resilient. This CRF technology allows engineers to finally design things the way nature does. We are moving from simply assembling different parts to actually growing distinct functions within a single form.
Speaking of things that are grown and hidden, we have to talk about the secret message aspect of this paper. Because you mentioned earlier that crystallinity changes how the material actually looks.
Yes, it does. Crystalline regions, the uncooked spaghetti, they scatter light. So to our eyes, they look cloudy or even opaque white. The amorphous soft regions let light pass right through, so they look completely clear.
So not only are you printing hard and soft, you are simultaneously printing white and clear.
Correct. And the researchers showed this off in a very dramatic, a very cinematic way. They printed these completely flat, uniform sheets of plastic. To the naked eye, sitting on a desk just looks like a plain piece of plastic. Maybe a little cloudy, but if you hold it up to a backlight.
It is a total national treasure moment. I love it.
It is. Hidden inside the plastic, purely defined by the cloudiness of the molecules, is the Mona Lisa.
And the creation of Adam by Michelangelo, right?
Right. They reproduce these absolute masterpieces with incredible detail. But there's no ink. There is zero pigment in there. The image exists solely because some pixels in the plastic are harder and therefore whiter, and some are softer and therefore clearer.
That is just showing off, honestly. But I absolutely love it. It proves the insane level of control they have. It is not just hard blob over here and soft blob over there. They have pixel-level control over the physical material properties.
It creates a perfect continuum. It's not binary. You have infinite shades of gray in the light, which translates to infinite shades of stiffness in the object.
Okay, so we have got squishy turtles. We have got Renaissance art hidden in plastic. But you know me, and you know the listeners of the Deep Dive Lab. We always want to know, can we punch something with it? Or at least, can it take a punch?
I had a feeling you would ask that. And yes, the researchers actually looked to the animal kingdom's absolute heavyweight boxing champion for inspiration.
The mantis shrimp.
The mantis shrimp, specifically its dactyl club.
For any listeners who do not know, the shrimp punches so hard and so fast that it actually boils the water around its fist. It creates these cavitation bubbles that collapse and generate heat hotter than the surface of the sun for a split second. It just smashes open clamshells. It is terrifying. It is like the one punch man of the ocean.
It is an unbelievable biological structure. And the reason the shrimp does not just completely shatter its own hand when it punches a solid rock at 50 miles per hour is because of something called a Boulogne structure.
Boulogne. Sounds fancy.
It is essentially a helicoidal structure. Imagine stacking flat sheets of plywood, but rotating each sheet just slightly as you stack them up. It creates this spiral staircase of fibers. This structure is famously amazing at absorbing energy and stopping cracks from spreading.
Because if a crack tries to form and go straight down, it hits the next layer and has to keep changing direction.
Exactly. It forces the crack to travel a much longer twist of path, which dissipates the energy. And let me guess, you know what is coming.
The Kirov team printed a mantis shrimp club.
They did. They used the light engine to print layers of pCOE, where the grain of the hardness rotated slightly with every layer mimicking the exact architecture of the shrimp's club.
So they printed a single material that is naturally shock absorbing.
Yes. They physically tested it against solid uniform blocks of the exact same material. And the Bulligan structure, the shrimp-inspired one, was vastly superior at dampening vibrations and absorbing high-velocity impact. It did not crack. It just ate the energy.
This is where it gets really interesting for you listening right now, I think. Because, yeah, a cool plastic turtle is fun, but shock-absorbing, shape-shifting material, that changes everything.
Think about helmets for a second.
Oh, absolutely.
Right now, a bike helmet or a football helmet is basically just hard foam glued inside a hard plastic shell. It is uncomfortable, it is bulky, and it's largely a one-size-fits-all approach regarding impact. Imagine a helmet printed with a CR5 towel lattice.
Soft and squishy against your head, so it is actually comfortable.
But progressively harder and more crystalline toward the outside shell for actual impact protection. All one single piece. No glue, no foam inserts.
Or shoe soles. I run a lot, and I would kill for a shoe that is incredibly soft in the heel for a nice landing, but perfectly rigid in the toe for a strong push-off.
And customized to your specific foot strike. You can take a 3D scan of your foot and print a sole that manages the kinetic energy perfectly for your unique stride. Currently, shoe companies have to glue different foams and carbon plates together to even try and achieve this.
And they always fall apart after a few hundred miles.
And when they do, they are completely impossible to recycle.
What about robots? We have talked about soft robotics on the show before. You know those robots that can squeeze through tight spaces or handle fragile things?
This is a massive game changer for soft robotics.
Yeah.
Usually soft robots are just floppy. They have a lot of trouble exerting actual force. They can wiggle under a tight door, but they cannot turn the heavy doorknob once they get inside.
It is the wet noodle problem.
Exactly. But with QuickCraft, you could print a robot that is flexible enough in the joints to crawl under a door, but has highly crystalline rigid bones embedded seamlessly inside so it can actually lift a heavy object.
A robot that is simultaneously a flexible tentacle and a rigid arm.
Precisely.
Yeah.
And let us circle back and look at the sustainability angle again, because that cannot be overstated. We mentioned earlier that gluing different plastics together makes recycling basically impossible.
Right, the toothbrush landfill problem.
With a craft-printed object, the hard protective part and the soft squishy part are chemically identical. They are both just pCOE. The only difference is how those specific molecules are arranged. So if you grind it up and melt it down...
It just goes right back to being uniform liquid pCOE.
Exactly. You reset the spaghetti, you can recycle the entire thing without having to separate any components.
That is a massive win. One material to rule them all.
It really fundamentally solves the mixed material waste crisis in manufacturing. If we could scale this out of the lab and into industrial massive printers, it changes the entire life cycle of consumer goods.
So let us recap what we have learned today, because this is a ton of science packed into a single deep dive.
Let us break it down into the main takeaways. First, we have learned that thanks to this incredible team at Sandia UT, Austin, and ASU, we can now 3D print hard and soft materials simultaneously using just a single vat of liquid.
And the secret sauce is just the light intensity. Dim light makes it hard like uncooked spaghetti. White light makes it soft like cooked spaghetti, which is honestly still the most backward, mind-blowing part of this for me.
It is wild. Second, this technique, CRFT, solves the recycling nightmare of multi-material products because it uses literally just one chemical compound to do everything.
And finally, it allows us to truly mimic nature. We can build things with bones and tendons and skin seamlessly connected, just like biology does, leading to vastly better helmets, robots, and maybe even the perfect running shoe.
Ultimately, it is a complete shift from assembling parts to programming matter. We are literally telling the material how to behave at a pixel level.
It really makes me wonder what is next. If you can program a material to be hard or soft, could you program it to change its state over time? But that is probably a completely different deep dive for another day.
One step at a time.
Mm-hmm.
But yes, the door is wide open now for materials that adapt dynamically.
Well, if you loved this deep dive into the future of making stuff, be sure to smash that subscribe button. Do not worry, your screen will not turn into soft rubber if you tap it too hard.
Not yet, anyway.
Exactly. But before we go, I want to leave you, the listener, with a thought-provoking question to chew on. We talked about printing turtles and impact helmets. But if you had a 3D printer on your desk right now that could print an object that transitions from rock hard to jelly soft in any crazy pattern you wanted, what would you build? Would you make a car bumper that actually bounces back into shape? What about a mattress that is ultra firm on one side and pillowy soft on the other, but has absolutely no metal springs inside?
I would personally print a coffee mug that is perfectly hard on the inside to hold the liquid,
Yeah.
but soft on the bottom outside so it does not clank when I set it down on my desk during a recording.
Oh, that is genius. See, the possibilities are just endless once you remove the limits of manufacturing. Think about it. Thanks for taking this deep dive with us, everyone.